Okay, welcome to class. Let me just make a quick announcement. There's about 7 or 8 people that still haven't gotten their clickers quite done right. And we figured out what it is. That most of the class did it, but a couple of you guys, if you haven't done so yet, you have to. So for example, if you have all zeros or all like dash marks or something for your clicker scores, then I'm talking to you. That should only be like 7 or 8 of you guys. You need to go to click modules here from the course website, and then you have to click this turning point clicker registration. What that does is it links your device, whatever you're using, your phone or an actual physical device, to your Canvas account. If you haven't done that, then your points are still being collected on my laptop locally, but I can't get them on Canvas without you doing that step. Doesn't matter, we'll still get your clicker points, but it'd make my life easier if you go to modules and click that registration link if you haven't done so yet. Again, that's only for the 7 or 8 of you that it's showing no points for. Sorry. If somebody has a stapler, this gentleman would appreciate it. Okay, we're going to start with our clicker quiz for today. And the first question is, what is the Weibull modulus? A measure of the variability of the color of a material, a measure of the variability of the ductility of a material, a measure of the variability of the strength of a material, or a measure of the variability of the crystal structure of a material. Okay, we'll get your answers in. I think one of these guys have a stapler. Okay, we're going to move to our next question. Weibull modulus. There was a reading. There was a reminder about the reading. We're going to keep going. Okay. Good. Either B or C would be a correct answer on this one. C is the more common one, though. Okay, how about this? Engineered ceramics have a Weibull modulus of approximately 100, less than 3, between 5 and 15, between 15 and 30. Okay, just another few seconds, get your answers in. Okay, we're going to wrap this one up. Okay. People think. Yeah, between 5 and 15 is going to be the most common for engineered ceramics. And then the last question for reading quiz is, samples with larger volumes will have lower strengths. A, true because the probability of finding a crack larger than the critical size decreases as volume increases. B, false because the probability of finding a crack larger than the critical size increases as volume increases. C, true because the probability of finding a crack larger than the critical size increases as volume increases. Or D, false because the probability of finding a crack larger than the critical size decreases as volume increases. Okay, we're going to wrap it up. Okay, ending it now. Definitely C. The bigger it is, Statistics just says the likelihood of your flaws being larger just gets higher and higher the bigger and bigger your component is. And sooner or later, that flaw is going to be bigger than the critical flaw size, so it's going to drive your strength down. Okay? All right, so what are we going to learn today? We're going to talk just a few more moments about creep in polymers. We'll just say a few words about hardness as a measurement and that it can help us glean some other mechanical properties. And then we're going to spend the bulk of today's class talking about variability in data, and we'll introduce Weibull probabilistic failure statistics, which in my opinion, this or free energy are like the two most important things you're going to learn this semester. They're just incredibly useful things to learn as engineers. Okay, so let's start with polymer creep. Creep, if you'll remember from a couple chapters ago, was time-dependent plastic deformation, right? So you apply a load and it doesn't happen immediately, but you see this plastic deformation occur over time. This is especially problematic in polymers because, again, you have this bowl of spaghetti, and if you apply a load to this thing, the noodles can sort of slowly slide past one another. The same thing can happen with your polymers. Because there's so many degrees of freedom where these things can move past one another, they're especially prone to time-dependent plastic deformation. If you've ever seen a car that's been parked for a very long time and then driven in it, it can have flat spots on the tire. That's what's happening there, right? That tire's been sitting there slumped, and especially if it's a flat tire, it actually is creeped, right? It's actually deformed. And so because of that, if you have a mobile home or something that isn't going to be driven very often, they'll actually put these flat stoppers on it just because they know that creep is such a problem in polymers, right? We're going to come back to something, creep compliance and basically something called stress relaxation in polymers next chapter. So we haven't seen the last of creep with polymers just yet. Let's talk about hardness. Hardness, if I were to ask you guys, you would all probably give me correct answers if I asked you what hardness is. But hardness is actually a tricky thing to define in material science. It's not straightforward because there's so many different definitions, right? You could say, okay, well, is it just how if you try to press into a material, it's the resistance to it being pressed into, right? Is it its scratch resistance? Is it this generic term of localized deformation resistance, right? All these are technically kind of true answers. So why we care about hardness is obviously you have things that you don't want to scratch, right? If you're designing some new iPhone and you want that anodized aluminum beautiful back cover that won't scratch easily, that's important. Or the screen, right, on the front side, the glass, you don't want that to scratch. But it's also useful as a characterization tool. Why is because you can actually test the hardness on a really small, even a microscopic section of your material, and it can tell you a lot about the bulk properties, right? So for example, how it's typically done is you use an indenter, you lower it onto the surface of your material with a prescribed load, and then you look at the indent that it creates. They can do that in different ways. They can either measure how deep into it goes, or you can indent it, pick your indenter up and move it, and then bring a microscope over and look at it through the microscope, and you can literally measure the size of this indent. There are instruments that work both ways. If you look at it under a microscope and measure it, that's the one on the left here. That's called Vickers hardness. That's a better method than the Brunel or the Rockwell hardness, which is on the right. That's based off of indent depth. That's easier, but it's not as high quality of a hardness measurement. But from these, you can actually back out lots of other properties. There are people that argue you can actually get fracture toughness out of this. For example, if you look at these things and you indent it, you might see cracks forming along these edges. And basically, the size of that indent versus the length of those cracks, people have used that to estimate fracture toughness. There's some question on whether or not that's totally valid. This has been used to estimate yield strength. Lots of different properties from something that's pretty easy to do. So as engineers, this is a useful thing to at least know is out there. We could do a whole class just on hardness and the different ways that it's measured. Just be aware that it's out there. And nowadays, we have nano indenters, which are they're just a whole lot better than the indenters of the past. And they're actually pretty cheap to use, right? We have one on campus that we just purchased, which is 10 or 12, 20 bucks an hour to use. Very, very inexpensive and gives you very nice data for hardness. So again, what's great about it is you don't have to destroy your material. You could take an individual component, do a tiny little dent that no one will ever see, and it gives you some degree of quality control. And on the concept of quality control, let's shift now to variability. So maybe to start with this one, a couple years ago, I spun the wheel over at the University Credit Union, hoping to win like season tickets to football, and didn't. I won a pom-pom, which was depressing. But we've put this pom-pom to good work over the years, and we're going to do it again today. So I need someone to come up and help me. Anybody? Yeah, come on down, Matt. What Matt's going to do is he's going to try as much as he can to be consistent each time, but he's going to grab one of these, and he's going to measure out, a few centimeters, make sure it's the same each time, right here. Measure out a distance between your two fingers, make it like 5 centimeters maybe. And then he's going to, at the same rate, he's going to draw that thing apart until it breaks, and watch closely how far it gets before it breaks. Don't do it too slowly or it'll just stretch forever. Okay. While he's doing that, maybe turn to a neighbor and tell me why will it just keep on stretching far, far further if you do it slowly? Yeah. 12 centimeters. Okay. Yeah, keep on doing it. Okay, anybody got a thought? Why is it if I pull that thing quickly, it's going to snap pretty short distance, but if I pull it really slowly, it's going to go a long ways? Anybody have a thought? Ryan? Kyle. Okay. Yeah. Imagine that you have like a bowl of spaghetti. If you just grab one noodle and you yank it really quickly, it's probably going to snap, right? Whereas you pull that really slowly, you're giving it the time for that thing to sort of do whatever it needs to do to slither past other noodles, right? So the same thing's happening over here. So we made it 12 centimeters. How far did the second one go? 20 centimeters. What about this next one? Each one of these, right? Yeah. Okay. That'd be good. So we'll do maybe one more. We're assuming that he's pulling these at roughly the same rate each time. 18. And that one made it 18. So thanks, Matt. That's perfect. So with 3 different measurements, and I assume when they made these things, they all came from the same batch. Some big sheet of this stuff, and then they cut it into little strips and put it into a pom-pom, right? And you're getting, even though these came from the same batch, they don't all elongate the same amount, right? You can figure out what the elongation is and therefore the ductility of these, and we're getting different values, like pretty significantly different, like 100% different in some cases, right? Almost. So this leads to the question that even when we have things that we've engineered and you'd expect them to be pretty similar, in fact, you can see pretty big differences in variability, right? Variability in data is a big deal in engineering, right? Same sample, careful measurements. You won't always get the same result every time. That could be strength, that could be elongation, that could be time until failure, that could be any property you want. There's always going to be some sort of scatter. And so the way that we've naively probably been thinking about that up till now is what? What do you do? Right? What do you do this? As engineers, what do you get to do? You've got a bunch of, your boss says measure this, you go and measure them, and then you report it. What do you do? Rose, what would you do? You're going to definitely give them an average, right? With these things, you could take the average of these 3, you'd add 12 plus 20 is 18, divide it by 3, and you'd have an average, 16 or something, right? So that'll help. An average is certainly a good place to start. What else can we do? Yeah. A range. You could give them a range. You could say that failure ranged between 12 and 18, 12 and 20, and that's helpful. It doesn't tell you an average, but it at least tells you a range. So actually both of those are useful. An average and a range are both useful. What else have you seen done? Yeah?
Take one of the low values and add some sort of safety factor to it.
Oh, okay. So now you've gone the next step. You've gone from interpreting your data to now analyzing and deciding what to do with it. So for example, take one of the low values, 12, and if you need your pom-pom to, whatever, this is kind of a silly example, but you could say, don't ever try and stretch this pom-pom more than 8 centimeters, right? Or something, some sort of safety factor, or it's going to break, right? Right? So yeah, that's another thing. What else could you do, Jeff?
You could say maybe like 25% break at 12 centimeters, 15% break.
Yeah, now it's getting better. Now you're actually breaking it down into some sort of fraction of failure. That's really useful. Yeah, Brennan? Standard deviation is probably the most common thing that you'll see. So whenever you see something plotted and it has error bars above and below it, more often than not, that's a standard deviation. That's just sort of what we do in this field. I think sometimes we do it without even thinking about it. That's just one standard deviation usually. Okay, so those are all useful. So I guess let me ask you this question. Which of the things we heard, is it more useful to say, what is the yield strength of this alloy versus what is the probability of yielding for this alloy under these conditions, right? Clearly that second one is more valuable, right? Because we know that a yield strength, if it says that this steel alloy can withstand, 400 megapascals, you're going to be a little bit skeptical and you're going to do what John did. You're going to say, yeah, but I'm not going to assume that it's going to make it to 400. I'm going to only load it up to 200. right? A factor of 2 safety factor. That makes us feel great. A factor of 2 always makes engineers feel great, right? So the question is, should we still feel great about that, right? Can we do better than just an oddball safety factor? And we can actually. So average is easy. Just sum them up, each individual part, divide it by the total number. You guys have all done this since grade school. Standard deviation is a little bit harder. Here's the formula. You're still going to sum something up. You're going to sum up each individual value, and you're going to subtract from each individual value the average value. And then you're going to square that. That's called a variance, right? When you square a difference, that's a variance. So you're squaring that. You're dividing that by the number of samples minus 1, taking that whole thing to the square root, right? This is the standard deviation that you've been using in Excel, maybe not even knowing what it means. So that is not the same as the range. So if you expect, like when you see data, right, whatever you're plotting, oops. No pen today? Hold that thought. Let me do my magic trick. Right? When you see data that's plotted, hopefully this works. No pen. Hold that thought. Wonderful. Give us a second. When you see data plotted and it's got error bars, I think a lot of us would assume that all the data basically fell within those error bars, right? But that's not what the standard deviation is telling us. That would be the range, right? And that's not what the standard deviation is. Hopefully this works now. Very disappointing. Maybe my battery died. All right. So we can draw it with our mouse, like barbarians. All right. There's our data point. There's our range, right? So that is not nearly as much information as actually was in what went into the test. When you tested this, maybe you tested 20 or 30 samples. This is just saying what the average was and what the standard deviation was, right? So we'd probably like to know more information than that. Let's see if you'd like to type in. Okay. So one way to do that is to do what Jeff said and basically talk about probability of failure at different amounts. So when they do this, you're usually talking about a distribution. And if your samples happen to fall under a Gaussian distribution, maybe you've heard that before, or a bell-shaped curve, if you've heard those talked about before, what that's doing is it's talking about, God, it's disappointing. It's basically saying that you have an average value at which they fail, and then you have standard deviations out to the left and the right. So for example, this one standard deviation to the right, and 1 standard deviation to the left. If it's a Gaussian curve or a bell-shaped curve, that should capture 68.2% of your data set. So this data point that we saw up here, that's not the full range. That's 68.2% of your data, right? If you've been using standard deviation, that's all that is, right? So then if you go 2 standard deviations, you've now captured 95.6, right? You're going from here all the way to there. That's 95% of your data falls within that range. 3 standard deviations, now you're at 99.8. So because of this, there's been something that's called 6 sigma. Anybody heard of 6 sigma before? Rob, what's 6 sigma in like a word? Or what context have you heard it discussed in?
Well, I've just sort of thrown around, but it refers, from what I understand, to like the general, just about everything.
You can use it for just about everything. Anybody have heard a place where it has been used?
What I mean is that like it refers to like just about all of your data.
Oh, gotcha. Yeah. So basically, if you're talking about capturing data, basically all of it is captured within 6 sigma. So in fact, it's 99.99966, right? So 6 sigma is basically all of it. Or in other words, there would be 3.4 defects per million, right? If you do 6 sigma. So let's say that you're making a car, right? And you need the airbag to go off all the time if there's a crash. Then you might apply 6 sigma principles to design your airbag in such a way that only 3.4 defects in a million will exist, right? Hey, there we are. The battery died. Okay. So 6 sigma, it actually was started by, let's see, who was it? It was started by, in Motorola in 1986. It was sort of made famous by Jack Welch at GE, General Electric, in 1995. And the idea behind it is that you systematically remove defects to improve whatever the outcome is you're talking about, right? So if you're running a plant and you're making steel alloys and you need 6 sigma to survive within some sort of range, you're going to systematically look at what's happening when you make that alloy to make it stronger and better, right? And you're going to slowly improve that process, right? Okay, this concept of a bell-shaped curve, where some of your samples, not very many, are going to fail at like a really low value. Some of them will withstand to really, really high values, but not very many. And most of them will be somewhere in between. That becomes important when we get into Weibull statistics. Okay, so most engineers, instead of doing probabilistic design, they just do safety factor design, right? It's exactly what John said before. You say, well, the spec sheet said that this thing can withstand acids for 20 hours. So tell our consumers they can only put it in acid for 10 hours, right? This happens with your phones, by the way, right? When you have these waterproof phones, it says, whatever the ISO test is for waterproof phones, it says 5 feet, 30 minutes, right? So they tested that, and I'm sure it was more than 30 minutes, right? But they tell consumers don't take it beyond 30 minutes because they don't want it to fail, right? So this is sometimes thought of as over-engineering it, or assuming worse performance, right? So for example, if your design stress, sigma D, that's the design stress that you're going to use, if that's equal to some sort of safety factor multiplied by the expected stress, then you've over-engineered it, right? So for example, if you expect to only see 100 megapascals on your component and you design it to withstand 200 megapascals, then you have over-engineered it, right? You put in extra material or whatever you need to do by a factor of 2 in that case. Another way to think about it is you say, okay, the yield stress for this alloy is something, so we're going to design it to be n number of times worse, right? So both of these, they're still not great because you're still just guessing. Like, why use a safety factor of 2? Why not use a safety factor of 3 or 10 or 100, right? You're kind of going off of your gut, and that's not the best way to design something if it's very important, right? If the airbag goes off, that's a very important thing. You need to have more than just a gut feeling that it's going to work each time. You'd like to be able to convince skeptical consumers and consumer reporting agencies that it's going to work every time, right? So there's a better way to go about this. So if you take nothing away from today's class than this, take away the fact that you need to not just use safety factors. It'd be better to be analytical and probabilistic about failure. And the best way to do that we're going to teach you today is with the Weibull modulus, right? So the Weibull modulus is given here. The expression is F equals 1 minus the exponential of negative, we're going to use strength, but it could be other things, strength at the failure divided by your characteristic strength, sigma naught, all of this raised to m, which is your Weibull modulus. So what are some of these things we're talking about? F is your probability of failure. So that's a number between 0 and 1, right? If F equals 1, that means that no matter what, every single component will fail under whatever the condition is, right? If F equals 0, then no matter what, none of them will fail. And it's somewhere between 0 and 1 for materials, right? 1 minus exponential, so sigma F, again, that would negative sigma S, that's the stress at which you're going to observe failure, the characteristic stress in Weibull modulus, okay? A higher Weibull modulus, so a larger value of m, that means that you have a narrower distribution. So let's actually draw this. If you have, let's say, number that fail, and you're plotting that against stress, you could have a narrow distribution, where most of them fail within a pretty tight band, or you could have a broad distribution, right? You could have something like that. Okay? They both would have the same average, right? They would have different standard deviations, right? We can actually do more than just average and standard deviation, though, if you define a Weibull modulus for this. You can actually capture the whole shape of this thing, right? So again, a higher Weibull modulus would be something like the red, and a lower Weibull modulus would be something like the blue there, okay? All right, what they normally do, just like with everything else in this class, when you have an exponential, we usually try and make this look linear. Yeah, question?
Can you interpret for me, just real quick, blue versus red, which is like a better? What do you want? Do you want a higher one?
God, it's a great question. We're going to give you an example in a minute, and it looks like this. In fact, yeah, let me ask you this question right now. If you had to design for some sort of component, let's say you had a material which was quite a bit stronger on average, like this, but it was kind of broad, right? You could use that material, or you could use this material. Which one do you choose to use, right? And by the end of the class today, we should be able to answer this question. The answer is it depends, right? If you just care about on average, then you definitely use the one that has a higher average strength. But if you're trying to answer the question, I can only have 1 in 1 million fail. Now you could imagine that it might be better to use the green one, because your failure probability of your black one extends further out in this direction. Does that make sense? So we're going to give you, I think, an interesting example of that by the end of class today. Okay? So the first thing we do with this Weibull expression is we're going to make it look linear. The way you do that is first by bringing the 1 over, right? So now you've just got this negative exponential, right? Then multiply both sides by -1 to get rid of that negative, right? So now you've got 1 over, or actually you can divide both sides by 1 actually. So that gives you 1 over 1 minus f equals the positive exponential of this term, right? Take natural log of both sides and that gets rid of the exponential. Take natural log again and that brings this m down, right? And you end up with this more useful expression here, right? So natural log of 1 over 1 minus your failure probability equals Weibull modulus times the stress at which it's going to fail minus Weibull modulus times the natural log of your characteristic strength, okay? So here's how it works. How do you practically do this when you're actually making components? The first thing you do is you rank your samples in order of failure, right? How do we define f? We define f as equal to small n minus 1/2 divided by big N. Small n is the rank at which it failed. Big N is the total number of samples. Let's pull this up on a spreadsheet. I think it's this one. Yeah, okay, so right here. So this is the example I was just describing. You've got 35 bars, right? It goes from A1 to A35, 35 bars. You have a tight but a weak distribution, or you have a broad, strong distribution, right? So these I just told it to give me a random number between 200 and 500. That's what you're seeing in that first column. The next column I said, give me a random number between 3 and 900, but multiply it by a random number between 1 and 3. That's going to make a higher but a more broad distribution, right? So these two columns represent this exact scenario right here, okay? So the next step, if you want to do Weibull analysis to this, you need to rank these things. So you're going to grab these things and copy them, and then you're going to paste them over here as just values. And when you paste them, that changes the values. Every time you do it, it reworks the worksheet. So these numbers have changed slightly because it randomly oriented, but it's the same principle. The next step is you rank them from smallest to largest, right? So even though this was like 253, 344, like all over the place, you rank them from smallest to largest for both of those data sets. Okay? Then you calculate f. And I said the way that we calculate f is you take the number, the rank, the first one to fail, that's 1, minus 1/2, and you divide it by the total number of samples, in this case 35. Okay? That gives you your failure probability. So in other words, at a low stress, what's your failure probability? A really low number, right? At a really high stress, almost all of your samples are broken, right? F is almost equal to 1. Right? This makes sense so far? Everybody follow me? Can I answer any questions so far on Weibull analysis? Yeah, Rosa?
So you on your H column when you said you were
Okay.
the number. Will you say that again because there were 2 columns? Did you calculate it twice?
Good question. It's the same for both because this doesn't use the strength anywhere. It just uses the rank, right? When you calculate failure probability, the only thing you know is the rank. These are both, you're right, these are 2 different strengths, but they're both ordered from 1 to 35.
Okay.
And failure probability doesn't care about the actual raw value of strength. It just cares about the order.
So it just says for the type and weak one, all those numbers will apply, and then separately for the broad strong one, those numbers will also apply.
Correct. Failure probability is the same for these because we, for both scenarios, had 35 samples that we tested. If let's say you only tested 20 of your weak ones, you would have a different F value. But in this case, we tested the same number for both. Everybody follow me so far? Okay. So then the next step is, if you want to do Weibull modulus, you needed F. We figured out F. Now we need to know, to make this look linear, we'd like to make this whole thing, let's draw this. We'd like this whole thing to be Y equals MX plus B, right? So we'd like to plot for X, we'd like natural log of our failure stress to be X. Fair enough? So again, if you come over here, we're going to plot the natural log of our failure strength. This time you have to have 2 columns, like Rosa asked. You have to have one for the weak value and one for the strong value. In both cases, you're just taking natural log of that value. Okay? Then you have to have, let's see. So if you've got that, if you plot natural log of 1 over 1 minus f against the natural log of your failure stress, you should get a linear line that you can fit with these values. So what happens when we do that? So this is what we get. So all I've done here is I've plotted, like if I grab one of these data sets, I've just plotted natural log of 1 over 1 minus f, that's our y value, against natural log of the failure stress. And it's kind of linear. And it's not perfect. These things, they're not usually perfect, but that's a pretty good linear curve. And over here, you've got a pretty good linear curve. If it's pretty linear and your R-squared value when you fit this is close to 1, all that means is that your data can be fit by the Weibull expression, right? If your data can't be fit with this, like remotely linear, if your R-squared value is like 0.7 or something, then you're not going to be able to do good Weibull analysis with it. But these are great examples. Like your R-squared value is above 9 for both of those, so you can do some decent analysis with this, right? So these are linear expressions, and we have 2 equations of lines up there, right? Any questions so far on doing this? So now's where it gets kind of cool. Okay. So from that, just from those equations of a line, all I have to do is I look and I say, okay, this equals y equals 4.5742x minus 27.011. Therefore, 4.572, let me actually do this. So in this case, in one of our samples, m equals 4.572, right? In the other sample, m equals 2.623. Okay? That's our Weibull modulus for these 2 different materials. Okay? So from that, now we can ask ourselves really interesting questions. Like we can say, in order to have only 1 in 1 million fail, what stress should we design for? And then should we use material A or B, right? Fair enough? Material A or B, just these 2 different materials. So how would you go about doing that? If you want to make sure that only 1 in 1 million fail, how would you go about doing this? Well, the first thing you're going to do is you're going to say, all right, if 1 in 1 million fail, then what's your failure probability? 1 in 1 e to the 6th. You could do 1 minus 1/2. It's not going to change the answer very much, right? 1 minus 1/2 equals f, right? You basically want the very first one out of a million samples to be the one that fails. So you've defined f, so let's see what that is. So that is 5e to the negative 7.
I have a question.
Yep.
Why did you use 1/2? What's that?
So in our failure, how we're defining failure probability, there's got a 1/2 in it. You could leave it off here, and it's not going to change the answer very much. Yeah.
So what does it matter that it happens the first time? Why can't it happen on the random time?
Well, we want this to be only 1 in a million to fail. So we want our failure probability not to be a number that's close to 1. We want failure probability to be almost 0. Okay. So this gives us an almost 0 number.
It doesn't necessarily matter the rank of it. It just matters.
Yeah, this is the rank. It's the first one out of a million samples that we test. Okay?
Oh, I see, because they're ordered. Yeah, got it.
So now we want to then convert this into natural log of 1 over 1 minus f. Right? So let's plug that in. We do natural log 1 over the quantity of 1 minus f. And I get negative 14.508. Okay? What's our next step? If we want to figure out what stress can this thing go up to, what do we need to do next? Maybe turn to a neighbor and tell them what you think you might do next year. Okay, what's our next step? We figured out our failure probability. We turned that into natural log of 1 over 1 minus f. What do we do next to figure out the stress that we can take these things up to? Anyone want to take a stab at this? What's our next step? Yeah, what do you think? Yeah, so what we're looking for in this expression in our Weibull modulus is sigma f, right? Ultimately, we want to get to sigma f, which is the failure stress. That corresponds to some sort of failure rate, right? So we need to solve for sigma f eventually. m times natural log of sigma naught is actually given in this fit, right? M times natural log of sigma naught is just this last term, right? Which we've already got. So we know what y is. We just solved for it. This equals y, right? So we can actually plug in and just go ahead and solve for x. So let's solve for x with both these two equations and see what x is. Yeah, Rob?
Just a second.
Yep. Yep. So we're going to plug in the same y into both of these two expressions. The two expressions I'm talking about are this one here and this one here. Both of these equal y. So plug in the same y for both of those. Solve for x. Remember that x equals the natural log of your failure stress. And tell me which one of these things has the lower failure stress. All right, so give that a shot. Okay, you guys getting the same things as me? When I punch these things in, I solve for x first, and then you take and if you're going to solve for the sigma f, you take exponential of your x value. And therefore, you find that the failure stress, in order to have 1 in 1 million fail, you can take it all the way up to 15.37, megapascals, or whatever the units of stress are here, right? With the weak material, with the tight distribution. But you can only take it up to 5.34 megapascals with the other one. Right? This is surprising, right? This basically says that, okay, of these two materials, if you care about things surviving at really, really low probability of failure rates, it actually turns out you should use the material that on average is weaker because it has a tighter distribution. That's surprising. That's very surprising. If you did your whole gut, factor thing, you're not going to get close. First off, you'll have no idea what stress it can go up to have some probability of failure like 1 in a million. And you would probably never guess that material would be better than the other one. But here we've definitively showed that the material that was weaker on average but had a tighter distribution, it can withstand 3 times the strength of the other one with the same survival rate, right? Which is pretty awesome, right? Yeah, Arthur?
Sorry, can you go through the math again?
Yeah. So the Weibull expression, let's start back up here, right? We're assuming that we can fit our data with something like this, right? That's an assumption. If when you do this analysis, when you try and get a linear curve and it's not even remotely linear, then you have to abandon. You'd have to fit it to something else, right? Many data sets can be fit with this, right? So to do this, you need to figure out what F is. If your boss says, hey, I need 5 samples in a million to fail and no more than that, then you would say, great, F is now equal to... You'd say, okay, if 5 in a million can fail, then you would say that F equals the 5th sample to fail minus this 1/2 divided by 1 million, right? So you could define F, and from that number you could then define natural log of natural log of 1 over 1 minus f, and that is equal to y in your linear expression, right? Once you have y, you go to your Excel sheet where you figured out the Weibull modulus and you say, these are just equations of a line. We know what the y value is, so I can just solve for x using that equation of a line. When you solve for x, you end up with some values, and you recognize that x is equal to the natural log of sigma f. We know that because that's it right there. That's x, right? So once you know that, you just take exponential of whatever x was, and that will give you, in this case, the strength that you can take it up to have that failure rate. Does that make sense? Yeah, Takara?
So is there a way to quantify an error for this?
Yes, we don't cover that in this class. Takara asked a really great question, right? Basically, like, so your boss says, okay, I need 1 in a million to fail, and you do this analysis with your 2 different materials, and you say, well, it looks like, material A is actually better. Your boss would probably be wise to then ask, what sort of confidence do you have in that, right? Are you sure? Are you 90% sure? So there are confidence intervals with that. And basically, the more samples you measure, the tighter your confidence interval goes up. We don't cover it in this class. In my ceramics class, we do. Basically, you need to do at least, like as a minimum, if you're testing samples, anything less than 20 samples has enormous has terrible confidence. It has really big errors associated with it. Above 20, and that confidence interval starts to get better and better. I think I'll post it. I have some subsequent reading I'll post for you guys. The more samples that you test, though, if you test 100 samples and you do your Weibull modulus after that, you're now approaching like 90% confidence intervals. Okay? Any questions I can answer about this? Yeah.
The whole map that has your Excel,
Okay.
which equation do you use?
So when I did the Excel spreadsheet, all you had to do first off is take whatever your value is that caused, this could be time until your phone dies underwater, right? You had 1 phone die after 1 minute, 10 phones had died by 10 minutes, all your phones had died by 30 minutes, right? Whatever it is, you're gonna rank them in terms of first to last, and you're gonna put these values in order from smallest to largest, right? You then do your failure probability by taking the rank divided by -1/2 divided by the total number, right? That's your failure probability. And then over here, you're taking natural log of whatever that value is. If that was time underwater until failure, great, then natural log of time. In this case, it's natural log of probably a strength in megapascals, okay? And then you just choose to plot this as your x value, this whole column as your x value, and this as your y value. And that's what this data is. As soon as you have that data, all you had to do was go add a trend line, tell it to do a linear one, tell it to show you the equation, and your r value, right?
So what's the y one? So the x one is the ln of what you found for the probability.
And y is natural log of 1 over 1 minus f. Again, going back to this math, that was the only way that we could make the Weibull modulus, which is not a linear expression. We can make it look linear if we took natural log of 1 over 1 minus f. So that whole thing, this whole thing over here, that's all just the y value on that plot. Okay? So again, that's all I've done here. Natural log of 1 over 1 minus your failure probability.
And so the weak and the strong, that's just from different numbers.
That's because we've got 2 data sets. One of them is a weak type distribution, one is a strong broad distribution. Right? Any questions on generating this? You're going to do it for your homework. It's the dreaded Halloween Weibull modulus problem. Right? Brings great joy every year. I get it. This is tricky stuff. It is one of the more valuable things that you're going to learn in this class. Like, hands down, this is one of the more valuable things that you're going to learn. Because you're not just going to be going off of gut factors. You can say with confidence probabilities of failures. Like, imagine now, let's go the other way. Let's say that this is your 2 distribution. Let's say you're just talking about the broad one for a minute. And your boss says, okay, in service conditions, you might actually have a stress that goes up to there. So what fraction of our components can we expect to see fail, right? Right? So how would you do that? How could you tell your boss, using this analysis, what fraction of your components will fail at some arbitrary stress? Let's say that this is the exact question. Let's see, what fraction of the components will fail at 100 megapascals? Okay? What fraction of the components will fail at 100 megapascals? So turn to your neighbor and talk about how you would go about tackling this question. Okay. What's the approach here? How would you figure out what fraction will fail? Rob, what do you think?
It's easy. You just do it backwards. So you plug that in for your sigma f and you work through the whole thing reverse.
Yeah, it's no big deal. In this case, you don't know what f is, right? If this is your expression, you eventually want to get to f, because from f you can get to a fraction that failed. Well, f is the fraction that failed, right? It's the percent failure. So you start with the stress, you plug that in, right? Plug that in as your x value, and it's straightforward. So let's do it for this one. 2.623x, right? So we'll say, okay, y equals 2.623 times natural log of 100. That's x, right? That's going to be minus 18.907. Okay? So y equals what?
Wait, I thought you said that natural log of the stress is x.
Yep.
So why does it equal y?
Natural log of stress is right here. This is x. This whole thing right here, that's x. And in your equation up here,
Oh, that's
you have the x.
equation.
Yep. No, you're good. So 2.623 times the natural log of 100 megapascals minus 18.907. Okay? That's negative 6.827. And you recall that that is equal to the natural log of 1 over 1 minus f. So let's solve for what f is. And f is equal to 0.001. Or in other words, multiply that by 2 and you've got 0.1% of your samples fit, right? This is really great. This is a really great tool, right? So this is no longer just gut feelings design. This is what we call probabilistic design, right? You take into account probabilities. You test a bunch of samples. You have some sort of expression that your data fits, in this case the Weibull expression, and now you can probabilistically talk about failure, and that's definitely a way better way to go. Arthur?
For the homework, are we also supposed to use Excel to do what you did?
Yes.
Are we going to have to learn how to use Excel?
All you had to do, the trickiest thing you have to do, if you take your data, it's not sorted yet. So this right here, you'll first need to grab this thing, copy it. I'm just going to put it right here for a minute. I'm just going to do a paste special. I'll make a video on how to do this after class. But you're going to paste the values, and now you need to rank these. So you go to sort. You're going to go from smallest to largest, and you're only going to sort just the data in that gray box. You're not going to make it stick with the stuff around it. So you continue the current selection, and now they're sorted, right? They go from smallest to largest. That's about the most Excel trickery you have to do on this. It's pretty straightforward.
Also, how to plug it in.
How to plug it? All right, I will do a subsequent follow-up video walking through this. Takara. If you want to do it in MATLAB or anything else, it's fine by me. I got no problems. Let me talk about one last thing here. We've got just a couple minutes left. Okay, let's say that you tested 35 bars in the lab, and they were the size of this battery. They were tiny, and you've got your Weibull modulus for these tiny batteries, right? And you're feeling good about it. But then your boss says, by the way, we're not making tiny things like this. We're making freeway overpasses, right? It's the giant column that's the freeway overpass, or something enormous. So how do you scale the testing that was done on a small sample to a really big sample? We know that when things get bigger, the probability of failure should go up because the flaw size statistically should go up. So we can account for that with a really cool expression. This is so neat. So this expression basically says at equal failure rates, right? So let's say that you tested these and you figured out what the stress would be for 1 in a million to fail, and it turned out to be that 5 megapascals or something, right? You now want to say, okay, what will be the stress that we can load a freeway overpass up to have the same failure rate, right? So the sigma of your component, which is going to be bigger than the bars you tested, equals the sigma of your bars, the stress that they could survive, but you have to multiply it by the ratio of the effective areas of those things, right? And raise that to the 1 over m. So I think we're out of time. Next class we'll do one last example of this where we take that into account. Okay, pick up the next time.